Okay, good afternoon. Welcome to lecture 13. So this is where we finally take a look at some transistors, at least physically what they look like and how they operate. So this lecture will be on MOS transistors, or MOS field effect transistors is what MOSFET stands for. Just some announcements. I guess last time, if you watched the lecture, the reason why things were going bad because the room was so hot. And I guess the projector overheated, and that was the problem. It was going in and out. There was no way we would have solved this, actually, except to turn the projector off for a long time, then turn it on, which is what effectively happened when I was doing the lecture by board. Projector was off, and then when I turned it on at the end, it started working again. But I don't think it would have worked that long. I think it would have stopped again at some point. So that's what happened last time, but I recorded the lecture. I did look to see how many people watched that lecture, and actually it's not bad. You are watching the lectures, so people are watching all the lectures pretty much. So if the room looks like this, which is very full for those who are watching by video, still people are watching the lectures nevertheless, which is good. So homework number 5 is online. It's going to be due via Gradescope next Friday. So lab number 3 is going to start next week. So the materials have been online. I think last time I said the pre-lab is due next week. No, the pre-lab is not due next week. This is also a multi-week lab, 2 weeks. So the pre-lab is due the week after next, and that's very important because you don't have all the material you need yet to do that pre-lab. So if you started the pre-lab and you were struggling with the MOS stuff, that's great because you need to do that anyway. You got a head start, okay? But, you know, like the last lab, you can get some work done if you just do some of the pre-lab. So try to get some of it done. I will not have lectured enough to at least get to the MOS resistor that you have to have in the lab. But see how much you can get done before your lab next week because, you know, that's time to do some of the lab. Okay, midterm 1, like I said, is 2 weeks away. Friday, October 11th. We have 7 to 9 p.m. in 160 Krober Hall. Trying to decide whether we use all 2 hours of that. Maybe we will. I'll make the exam for an hour and a half, but I'll give you 2 hours to do it. Because my ability to make an exam for an hour and a half seems not to be so good. In other words, I try to make it an hour and a half. Everyone ends up taking 2 hours anyway. Okay, so maybe we'll just use that whole 2 hours. I said this last time, but my Monday office hours will be from 5 to 6 p.m. on October 14th. Okay, so not next week, not the week after, but October 14th. They will move to 5 to 6, which is basically after lecture. Okay, so Monday after lecture will be office hours. Before the midterm, though, I'll have extra office hours. I'll hand out a sheet, actually, that gives you all the rules from the midterm, whether you can bring, you know, what cheat sheets you can bring, how many hours. We'll have extra office hours. We'll have a review session. One thing I want to ask, since all the class is here, and you can all put your inputs in right now, how would you like your review session? Can we do it on just the discussion sections that we have, like one review session on the Monday discussion section, one on the Wednesday discussion section? Will that work, or, you know, will that not work? Can all of you go to both discussion sections who care about the review? Is there anyone who cannot go to both discussion sections? Just raise your hand. Just say, really? You cannot? When is it? 9 to 10? Okay. All right. So we can't do that. We cannot do so we have to find some other time to do the discussion section. And I guess that's going to be late in the evening. 7 o'clock or something like that. Because that's the only way we're going to find the time that everyone can go to the discussion section. Okay? All right. So that's what we'll do. Because right away, not everyone can make it to both discussion sections. We could also do the review such that the review is mainly just your TAs asking you, would you like us to go through certain problems or so. We've done that in the past as well. And so in that respect, we could do it during the discussion sections. But it looks like so many of you can't make one of the discussions. That's got to be the Monday discussion section, that we'll just find another time to do this. Okay? Other than that, let me see if there's any other logistics. I think that's it. Anything else? Any questions about anything? Okay, so let's go on to the lecture. So again, the lecture topic today will be MOSFETs, structure and operation, the regions of operation. First one will be the cutoff region and then the linear region. And so before doing that though, let's take a little look at what we did last time, which was we finished diodes. And the last thing I was doing was sort of showing you the physical structure of an actual diode that's an integrated circuit diode. And so you can see the way that we make the diode is not taking a P and an N piece of material and sticking them together. We start with silicon, we diffuse in an N-type junction here, and we diffuse in N plus and P plus regions, where the plus means that they're heavy concentration. I think I should also mention here, while that I have this in front of me, that the substrate itself, the silicon substrate, this is usually a P minus material. Okay, if I make my diode that way. And the minus here, that minus means the opposite of the plus, so it means low concentration. Trying to debate whether I should fix that so it looks like concentration. I guess I will. Okay, and so I've got some regions of heavy doping concentration, some regions of light doping concentration. And the reason why I have the heavy concentration N plus and P plus here is that when I heavily concentrate my doping regions, that allows them to connect better to the metallization in this case. So this is metal right here. Right, this is a drawing that I drew last time. I'm just adding things to the drawing. Right, so the plus concentration means that I can make better contact to the metal. So maybe I'll say that. So that's better contact to the metal. And the metal then goes to the leads of this thing, which then allows me to access it from the outside. Maybe I should also say what I mean by high and low concentration. So high concentration means that I've got a concentration on the order of 10 to the 19th dopants per cubic centimeter here. So N-type dopants, meaning phosphorus dopants or arsenic in this case. A low concentration down here means that maybe I have 10 to the 15th per cubic centimeter. So 10 to the 15th still is a big number, but that's 4 orders of magnitude smaller than 10 to the 19th. Okay? And so then I've also got this N by itself. There's no plus and there's no minus next to it. And so this is going to be on the order of 10 to the 17th per cubic centimeter. Okay, so those are typical concentrations there. And of course this is a diode, so that's a depletion region. And the depletion region, as you saw in the last lecture, is where all the action occurs. Right, so let me just add that. Okay, so I've got all this structure here, but everything is really happening right here around that P plus junction. Okay, because that's where the P and the N really meet. And so that's where the diode really is. I guess I can also label, this is obvious, but this will be the N and the P junction of the diode. So I'm really looking at a diode like this. From that point to that point, the diode is kind of looking like that. Okay, on this. And it's planar in this case. And I guess when you look at it from a top view, what this looks like is this. So when we're doing these semiconductor type devices, the first thing you do is you lay out everything on a computer program. And so you're really just drawing the structures, but you're drawing the top view of the structure. So in this case, this diode is going to look like this. So I'll have my N plus part there, my P plus part there, and that's kind of, my N part would be right here. That's my diode there in the top view, or what I can call a layout view when you actually implement this, because that's what you're going to lay out when you're trying to make this diode. Okay, and so this drawing that I have at the bottom here is really taking a cross section through this, which I can like this. So that cross section is what I'm drawing right there, right? The side view cross section that I have. Okay, so that's the structure of the diode. So why did I want to go through all that there? It's mainly because when I talk about my my MOS transistor, this is what it looks like. Okay, so in a perspective view schematic, this is how my MOS transistor looks. And so what do I have? I've got some, well, first I got silicon here. And so that silicon is dope P-type. So that's boron doped silicon maybe. And then what I do is I diffuse some junctions just like I did for a diode. You can see two N+ junctions there. But I have more structure to this now. I have a metal on top of my source and drain, just like I had metal over the diodes, because I need to make contact. I need to connect that to somewhere off chip, or maybe somewhere on chip. I also have, I guess, what's being called metal right here, but oftentimes this gate is not metal. So for the longest time, this is called the gate. That's what the G stands for. And that gate has for the longest time been polysilicon. And the reason for that is I can grow polysilicon over oxide, which is what this hash line is right here, without creating too many interface states that would ruin the performance of the device. These are things that you would learn more in 130 and 143. But historically, this has always been called metal. And so that's what MOS means. It means metal oxide semiconductor here. And so I can go out here. That stands for metal oxide semiconductor. And so there it is. There's your metal, there's your oxide, there's your semiconductor. This is where most of the device action is going to happen right there. Okay, and that's what we're going to be very interested in, what's happening in the silicon at that point. You notice it also has a backside contact. So this is a contact to the bulk silicon, which is P-type. And in the end, that's the structure of our MOS transistor. And so I can also show this to you in a cross-section. So if I take a cross-section down the center of that other picture that I took, and so let me go back and show you this. So I'm taking a cross-section right down here, right across there. Actually, you could see that cross-section there as well. But if I do that, I end up with this. Right? So there's my N+ regions. There's my metal oxide semiconductor region there. And all the same stuff there. I'm not going to stare at this too much, because what I want to do is actually draw this for you now, because it's kind of instructive. As I draw this, it can really bring home the different pieces of this device. So let me move on to here. I guess before doing that, so I just showed you that MOS device. I guess I have this little out of order. I wanted to go to this first here. But let's talk about, because what that MOS device is a transistor. Okay, so let's talk about what a transistor is and why we want transistors. Maybe not yet the why we want transistors, but what it is. And so I can make a transistor either using that structure that I just showed you, or using another structure that's called a bipolar transistor. Or there's other ways to make things that are transistor-like. So tubes, vacuum tubes, for example, that are used in music and old television sets and old radio, they're also like transistors. They're sort of trying to do the same thing. And so the basic goal of a transistor is to create a device like this, where I have two terminals through which a current can flow, and I'm going to control the amount of current that flows through those terminals with a voltage at this terminal G. Okay? That's all a transistor really is. I have two terminals that I want to control what the element is in between them, and I want control through a voltage. So in this case, I've actually put a supply voltage VDD up here. I put ground at the bottom, which means current always goes from the high voltage to the low voltage. So current is going to flow from D to S in this case because of the voltages I put around this. And so with this device here, there's going to be a number of cases that I want. I want to be able to turn the device off. And so turning the device off, to me, means actually shutting down my VGS in this thing. And so I've got a voltage here, VGS. Oops. Too thick. No, it should have been thin. Okay, it is thin. Okay, so I have this voltage VGS that I have here. That's actually my control voltage, right? I can't just say voltage at a terminal. Voltage is always between two terminals, right? And so if this is ground, then I have a voltage VGS. If VGS, which is V voltage at G, minus the voltage at S, okay, if that's small, then I shut this off. And by shutting this off, what I mean is these terminals are like open circuited here. It's like they're attached to nothing within this device. This is the off state of my transistor device. And all transistors will have some kind of off state. I want to be able to shut it off. Okay? The second thing I want is to have some medium state or fully on state. And so what this is that when this voltage VGS becomes greater than my threshold voltage VT, okay, then this actually turns the device, quote, on. And what it means to turn the device on is I have some resistance now between my drain and source, which means current can flow. Okay, and notice I've drawn this resistance like this. It is basically a nonlinear resistor because now the value of that resistance depends on the value of my voltage VGS. Okay? And if I can change the value of that resistance based on VGS, that means I can regulate the current flowing from D to S, provided VDD stays constant. Right? I can regulate that current just by changing this resistance value. And this resistance will not generally be linear with this voltage. It will be some function of that voltage that's going to be nonlinear in this case for this transistor. For any transistor, it's generally nonlinear. Okay, now there is a case that you see in digital electronics where I make VGS so large that essentially this looks like a short between the drain and source. Okay, so again, that's my VGS. And if I make it large enough, then this is going to get to its lowest resistance. And it's going to look almost like a short. And so that's the regime that a digital circuit works at. A digital circuit works either in this regime up here or this regime down here. An analog circuit works in this regime. So that's analog. This is more a digital regime. And this also is more a digital regime. So immediately with transistors, one thing you have to think about is that they have regions of operation. They have this cutoff region up above, they have this medium region, and they have this fully on region. And we'll talk more about regions of operation later on. But now let's get back to our discussion of the MOS transistor. And so let's go here, and let me now reconstruct that MOS transistor for you, but sort of in a nice slow fashion here. One, so that you can get used to my drawings of MOS transistors. And you can get used to drawing them yourself because you're going to need to do that at some point in this class. So the physical structure, we just looked at the physical structure using the 3D and 2D pictures there, but now let me make this drawing. So first of all, I have silicon. So I'm going to draw a slab of silicon, and that's it. And so this is going to be like those other nice illustrations, a p-type silicon substrate. Okay. And this substrate is one of the terminals of this device. And so I can put a piece of metal back here. So that's metal. And that then will become a terminal. And I'll call that my bulk terminal. So that stands for bulk in this. The voltage there I'll call VB. Okay, and I can have a current going in there, which I'll call IB. Okay, so I have this as a p-type substrate. I also can make this p minus too. So often you'll see that p minus, much more lightly doped than the other parts of this. Now, that's the substrate. For my actual device, I'm going to have what's called a source which is an N plus region. Okay, it's going to have a piece of metal above it too, so that I can make contact to it. And so I'm going to call this S. For my source junction there. Okay, why am I calling that the source? Because when current flows, this will essentially be the source of my carriers, either electrons or holes. In this case, it will be electrons. And again, this shaded piece here is metal. So that's metal right here. And that's my N plus junction. I'm going to create another N plus junction back here. Put a piece of metal on that to make contact to it. And show its terminal there. This is now what's called the drain. All right, so I have a source of electrons, and like water, I'm going to drain them at the other end. I'm going to collect them at the other end. That's what this other N plus junction is. And so between the two of these, I have my gate. So my method for controlling how much current will flow. And that gate is effectively a conductive portion up here. Right, so this is actually a conductive portion that's either a metal or a heavily doped polysilicon. So I'll call this my gate, G, and I'll just indicate that this is heavily doped polysilicon. Polysilicon just means that instead of a single crystal, I have many small crystals of silicon that have been compacted together. Okay, and so by heavily doped, that means I can also call this an N plus region here. This also nowadays is becoming metal. Okay, so we're able to use metals now as gates nowadays, but right now we'll just talk polysilicon because that's what your book does. I can call this voltage VG, and this voltage I can call VS, this voltage I can call VD. Okay, and I'll have a current flowing here, maybe, that I can call I sub G. This current here is the current really that's going to flow generally between the drain and the source. So oftentimes this is going to be called IDS. That current right there. Okay? And let's see, do I have everything? This portion right here, that's really the, well, before that, this right here, as you indicated in those other illustrations, this is the oxide. Okay, that's a dielectric, right? Or it's an insulator, you can call it. Because of that, you don't really get current going through the gate, at least not DC current. So this IG at DC is going to be 0. But at AC, it doesn't have to be 0. You can get current going across a capacitor. Okay, so this now is a channel. That channel is where all the action takes place in this MOS transistor. Okay, so there's where I've slowly sort of illustrated the MOS transistor. Hopefully that was helpful in you understanding the structure of this device, which you're going to see again and again. But what you're really going to see when we talk about these is its actual symbol. Okay, and so there are several different symbols for an MOS transistor, but the one we're going to use is this. So if that's the gate, if that's VG, and the source is on that side, then we basically indicate the source by an arrow. So I've got an arrow coming out there, which means that this is the source. So that'll be V sub S, that'll be VD, and then finally we indicate the bulk by a terminal coming out of that. Okay, so this arrow there, that corresponds to the source, and so that tells you, if you know where the source is, you know where the drain is, right? Because the drain is just on the other side. But that arrow tells me where the source is. And in general, the reason why we make that arrow is because when we're actually drawing circuits, that's going to be the direction of current. Okay, under normal flow, that arrow will tell you the direction of current, so that helps you quite a bit. All right, so that's the physical structure of the device. Now what I want to do is just throw at you the equations that define this device. So I'm going to throw them at you now, and then we're going to derive each and every one of these in each of these regions. So don't be too alarmed by the fact there's a lot of stuff on this slide right now. But this defines this device. Okay, I've basically redrawn right here everything that's down here. Now with all the different currents, I've got maybe a gate current going there, maybe a bulk current going there, but certainly an IDS that'll go from drain to source. And that would be my drain source voltage across that, and then so little VGS, well, VGS here is going to be an important voltage, and so is VDS. So it's just like that generic transistor that I showed, except now I'm showing it with the MOS symbol here. Okay, and so here's how this thing behaves. In the cutoff region, meaning I'm going to take VGS and put it below some kind of threshold voltage. So that VTN there, that is a threshold voltage. And that's often going to be on the order of 0.7 volts, but it actually will change depending on how we've biased this thing up. Okay, but if VGS is less than that threshold voltage, maybe I'll indicate like a 0.7 volts there, but it's around that. It could be greater than that too. But when I have VGS less than that, no current flows through this device. Okay, so it's just like the transistor we want. In fact, let me put the transistor we want back up here, right? When I have this, I effectively have this equivalent circuit on the right. Okay, so the MOS transistor does exactly what I want it to do if that thing on the right is my definition of a transistor. Okay, but if I raise my voltage such that my voltage is now greater than VTN, so right, so now I'm saying VGS minus VTN is greater than 0, okay, but is also greater than the voltage VDS that I put between the drain and source, right? So if the drain source voltage is very small, then I'm in what's called the linear or triode region for this transistor, and basically I'm going to get an IDS that's given by this equation here. And so it looks like a pretty complicated equation, but before all is said and done, you will know what mu n Cox double prime is, you'll know what W over L is, you'll know what, you already know what these voltages are right here, but you'll know why it is that this takes this form. And I've written this also in another form where you can see that K sub n is the same as mu n Cox times W over L, so that these equate right there. Okay, but the other thing I can say about this, the reason why I want to write it this way, is that I can also multiply through and write this as K sub n times this VGS minus VTN times this VDS. I'm multiplying through this by VDS minus VDS squared over 2. Okay, and if VDS is small, then I can neglect that term. And then this thing really does look linear, right? It looks like I just have a constant term right here that depends on VDS in a linear fashion. So it now looks like a linear resistor made up of whatever this current is over VDS, right? So I could say that R, if I define an R equal to VDS over IDS, right, then from that equation here, that looks about linear, right? So it looks like a linear resistor in this regime when VDS is very small, and so that's why it's called the linear region. This actually is the region that you're using most often in your lab number 3. Okay, so your lab number 3 uses the device in this region here, and so that tells you sort of how to do that lab number 3, but you know, you don't nearly have enough information to get all of that pre-lab done. Okay, so the third region is the saturation region. Okay, so the saturation region, this is now where you still have VGS minus VTN greater than 0. It's over that threshold voltage, but now VDS is big enough that it's bigger than VGS minus VTN. Okay, so when that happens, the current characteristic changes to a square law function of VGS. And it no longer really depends on VDS much. It has a very small dependent on VDS because this lambda is a very small number. Okay, so that lambda, that's very small. So it's going to be on the order of 0.03 or something like that. So this will have almost no contribution. And so this now has a square law. This current now becomes a square law function of VGS. Okay, that's when the thing is strongly on, and that's when we call it saturation. Now I've got all these constants here, the Kn, the mu-n, the Cox. I'm going to define them for you right now. I have prepared definitions right here. Okay, so Kn equals all this stuff, this function of mu-n Cox. You've seen mu-n before as mobility. Cox is the gate oxide per unit area. Vt0 is the threshold voltage at a voltage VSB equal to 0 volts. Gamma is a body effect parameter. 2 phi f is a built-in potential, usually equal to about 0.6 volts. But that's a lot of stuff there. Okay, and I'm just throwing it at you now. Again, after a few lectures, it's going to take us a few lectures. You'll know exactly where all this comes from. But I'm just presenting this to you now so that you have a reference point of where we're trying to get to. Okay, we're going to derive all this now. All right? So before starting that derivation, let's review one thing about capacitors. And if you understand this about capacitors, which you do, but I just want to put it in your mind so that you recall all of this, you can understand everything that I'm about to tell you. The physics is going to start to get what you may think is hairy. In fact, the last lecture, if you watched it, may have seemed kind of hairy in terms of the physics. Was it? What did you think? You all watched it, right? Or are you the two that didn't watch it? Yeah, you all watch it, but it started getting kind of hairy, right? And some of it I couldn't explain in great detail because, like the injection, Fermi-Dirac statistics, those are things you learned in 130. But for the MOS transistor, I'll be able to do a lot more because this is more direct physics and Gauss's law and integration that hopefully you've had in at least your high school physics courses, right? You've all had Gauss's law, right? Poisson equation, yeah, you know all this stuff. But, you know, if ever you get lost in this, this is all you have to remember. If I have a capacitor like this, and if I put a voltage across this capacitor, like this, and say I call that voltage VG, what's going to happen in that capacitor if I put that voltage across it? I'll build up an electric field, yeah, that's true, and we'll be using that. But what's the other more important thing is I build up charge on those plates, right? All I'm doing is putting charge on the plates. If the positive terminal of VG is there, then I just put some positive charge on the top plate, and I'm putting some negative charge on the bottom plate. That's all that's really happening in a capacitor. I've induced plus Q here. I've induced minus Q here, right? So the plus Q there, you could say, induces the minus Q, or they induce each other, right? They're both induced by the voltage, and this minus Q is going to be equal and opposite to that plus Q. You always have to have this, right? And the equation for that Q, that has to be equal to the capacitance, which is effectively what this is, right? It's a capacitor, times that voltage, which in this case is VG. Okay, you remember this? Everything I'm about to do, you can simplify in your mind by quite a bit. Okay, so just keep all of this in mind when I start doing this to these somewhat complicated structures. Okay, so let's go to that cutoff region. This is the region where the device supposedly is supposed to be off. Okay, and for all respects, it is going to be in an off region. But what's happening in this cutoff region? So what I'm doing, right, let me first apply my voltages to this. So I'm going to have ground to my body, or my bulk. Right? Let's ground everything out, because we're going to cut this off anyway. So I'll ground that, but I won't ground my gate voltage. Actually, I will. It's like I'm putting 0 volts on it, but I'm going to allow for voltages less than VTN. Right? 0 is less than VTN, where VTN, like I said, is about 0.7 volts. It could be 0.7 to 1.5 volts, sort of like that. But here, I'm going to allow for that by saying that I'm putting on this node a voltage VG. Okay, so I put VG on that node right there. What happens to this? If I think of this as a DC condition, then this current, I sub G, has to be equal to 0. Right? So in this case, no current, no DC current flows into a capacitor. Because if you think of it, that's all this is. This is one conductor of my capacitor. This is my oxide dielectric. This is the other conductor of my capacitor. Right? So I'm really putting positive charge on this. And so let me just make this clear. This is for VG is less than VTN, which is set up there. Right? But I'm really just putting positive charge on this capacitor. So now let me use some of the stuff at the bottom here. And I can number this like I was doing in other lectures. So the first thing, I apply this VG. It puts positive charge on the gate. And this induces negative charge on the other side of the oxide. So let me call this 1. And so 1 is this. I'm applying that VG to that. And so now I'm going to induce positive charge. So just like the capacitor on the right, I'm putting charge right there. And the charge, of course, is going to want to hug the interface to the other side, because the other side is going to have negative charge. Okay, but here's where this differs a bit from this capacitor here. The capacitor that I'm showing there, if these are metal plates, that negative charge I have in that capacitor is basically just electrons on a piece of metal. Okay, the negative charge in the semiconductor, right, I could try to create some electrons down here, but it turns out the easiest way to create negative charge in the silicon is for the holes in the p-type substrate to move away. Okay, so this is a p-type substrate here, again, so this is p-type silicon. It's filled with holes as majority carriers, so they're free to move around. But when I put this positive voltage or positive charge on my gate, what's going to happen is my holes that were originally there, they're going to want to move away, because the positive charge is going to repel them. So holes are just moving away from that interface there. And they're going to leave electrons. And the types of electrons they're going to leave are, I guess I'll keep using red, are static negative charge, right? So it's just like the p-n junction. When I move the majority carriers away from that junction, what's left is the opposite charge, right? So I move these positively charged holes away, I'm left with negative charge there, and it's static charge. It's a depletion region is what it is. Okay? So I effectively, when I have positive charge there, I effectively have created a depletion region that's, say, that thick there. Okay? You also know that between this N plus and P junction, I have depletion region, right? And so the depletion region will have some positive charge on this N plus side. Right? And positive charge on this N plus side. Do that, finish that. And the depletion region on the N plus side, because it's N plus, it's heavily doped, is going to be very thin. Right? So I have this depletion region on the N plus side very thin. Right? And those will be positively charged, but on the P minus side, or sorry, on the P side, because it's less heavily doped than the N plus, this is going to be a thicker depletion region. So I can sort of draw it like this. And this will come in and connect with this depletion region right there. Right, so all this now becomes negative charge, negative static charge. So when I put the circles around this, that means it's static, it can't move. And that's what my MOS transistor looks like after I've just put a little bit of voltage on it. Okay, I haven't put enough to get over the threshold voltage, just a little bit of voltage on it, and so it's off, right? Because this region in here is a depletion region, right? So inside here, that's a depletion region. That means current doesn't flow. Current won't flow. I can put whatever voltage I want across VD to VS. Nothing's going to flow there because I don't have any free electrons or free holes to move that current across. All right? And so I guess to finish my picture, that's one. Two I just drew here, right? 2 is the holes moving out. 3 on this is a negatively charged depletion region forms. Okay, because it's simply just the easiest thing to have happen. And so I guess I'll say 3 here in point. Right, so I get that depletion region. And then 4, right, this is fixed charge that cannot conduct a current. I don't know how I'm going to do the 4. I guess the 4 I'm going to do like this. IDS is going to be 0 because of 4. Okay? And so that's what's happening in the cutoff region for this MOS transistor. Right? It's the simplest region, no currents flowing, but you can see there's a lot of stuff going on in terms of depletion regions and charge moving in different things. But the basic thing is this positive charge up here, the plus Q, has to be equal to the minus Q that's in the depletion region. Okay, so if I wanted to show this as plus Q, you do that in brown here. Whoop. Wow. This plus Q up here has to be equal to the minus Q here. Those two have to be equal between that. All right? Remember that, and you'll always be able to sort of keep the complexity under control, because it's going to get even more complex now. So let's talk about what happens as we try to raise that voltage even more. Okay, so as VG rises here, I guess I'll redraw a lot of this in here. So as I raise my VG to make it greater than VTN, guess I'll say greater than or equal to VTN. Now I'm over my threshold voltage. So what that means is I put more voltage on this. So I still have my plus charge here, but I've got more of it. So I'm going to show more of it by just putting 2 layers of plus charge in my gate. Okay, I have more positive charge. The other side I have to equate with more negative charge. And so what will happen at first is the depletion region will grow to accommodate, right? Because I've got to pull out those holes, so more holes will come out of that region. And the depletion region that I had there will now grow to a bigger size. Okay, because I put more voltage up there. I need more negative charge there. But at a certain voltage, explicitly this VTN, what happens is these holes are getting farther away. So the fields of my positive charge, going from positive to negative charge, they're very weak out here. As that distance grows, it becomes harder to push holes away in order to get that negative charge. And so what it does instead, it starts stealing charge from the N plus junctions out here. Okay? And so suddenly, instead of more of this static charge forming, I now form what's called a channel. So that red now is a channel of electrons. Mobile carriers here. And what that's called in MOS language is an inversion layer. And we call it an inversion layer because it has inverted the type of silicon that we have. Remember, this was P-type silicon. It was filled with mobile holes. But by putting this voltage here, we put enough voltage to invert this to something that's now full of mobile electrons. Okay, so that's why we call that an inversion layer there. And so basically, I still have these depletion regions here around all these things. Right, I still have my negative charge that's happening because I have PN junctions around my source and drain here. Still have that negative charge, but the more interesting thing is definitely the fact that I have this inversion charge. And if I put a voltage across this, so say I put ground there, and I put a VD there, but let's say it's a small VD, right, and I'm still grounding my VB in this case, okay, then what happens here is I will actually get current to flow. So now I get current to flow because I have these mobile carriers that can actually move with that field. So IDS now becomes something finite. And so all that I said is actually written above here. So we're at more positive charge here. You can label that 1. So So I'll label that 1 right there, leads to a depletion region of negative charge that grows. So this has grown, say, from its original thickness, which was there, to there. So I grow that depletion region there. Okay. Soon the depletion region becomes large enough that it becomes easier to obtain charge by taking it from the source and drain region. So 3 is sort of this channel of electrons that occurs. That's 2. No, 2 was here. So 3 is this depletion region forming, but I guess I could put that 3 right here, right? That it can't push the holes out anymore, any further. So 4, it creates that channel of inversion, that channel of electrons, the inversion layer there. Okay, so that's what's happening now for the linear region of this thing. So I'm keeping V sub d small. So I'm trying to stay in the linear region, which means I'm trying to stay in that region. I'll go back to this here. So I want to stay in this region. So I'm saying VDS is less than VGS minus VTN. So it's a small VDS. It's not this case yet where VDS is large, but it's this case where VDS is small. All right? And so with that, that's what I'm going to now analyze. Okay, so I now want to go over here and actually analyze this whole thing to derive the expression for this current that goes through that. So I'll start this analysis right now. So I've got this channel of electrons and an E field generated by VDS gives rise to drift current flow. Channel of electrons, I guess, I want to be complete. I should say that's also 5. And then IDS will flow here as 6. So I can do 5 and 6 right there. Okay? I have this current flowing there. I should go a little IDS to be and that's a finite amount of currents, not 0. Okay? So now what do I want to do? Now I want to derive how much current IDS flows as a function of my voltages. Flows as a function of voltage. I should say voltages VGS and VDS. Okay, so this is going to now be a formal derivation for all of these things here. And so I have an expression for current here. I guess before that, let me ask, are there any questions about what's going on here? So all this stuff that I'm doing here. Anyone have questions? Want me to clear anything up on just this stuff that you see on your right or in the cutoff region? Yes? Yeah, there's no difference right now. But there will be a difference. Well, I guess the difference is the following. So when I apply a positive voltage between VD and VS, right, then my electric field, this is green, is going to be in this direction, right? So I basically create an electric field between VD and VS. What's the best place to put that? How about here? Right? If that's my electric field, then the electrons are going to be moving from left to right, right? And so you can call this the source of electrons. Right? The electrons are coming from here, and then they're draining out here. Right? So that's why we call it source and drain. So this is my source of electrons that flow across the channel, and then this is my drain for the electrons once they've crossed. That's why we call it source and drain. If this were a P-type device, which it can be, I could put a P plus in these source and drains there. Then it'd be the source of holes would be on the left side. Right? So the left side, at least the way I'm drawing it, are always the source. Okay? But if I flip these voltages, you're right, it's purely symmetric. If I flip the voltage to put a larger voltage here than here, then this becomes the source on the right. Okay? Any other questions on this? Ask if you have a question. Okay. If you do have remaining questions, then come to office. Usually people have questions at this point. You know, they're confused about different things on this. So don't be afraid to ask if you want to ask a question about this. But right now, let me at least just start this. I guess this is the last thing that I'll leave you with here. And that's that if I have electron current, and this is a current that's moving because of voltage. What do we call a current that moves because of voltage? We've got two types of currents. Drift and diffusion. This one will be moving because of a voltage. Yeah, right, drift. Okay? So the electron drift current at any point in the channel is going to be given by an equation that we've seen before. I of x is going to be equal to whatever the charge density is, and this is going to be charge per distance is what the Q prime is there. So that will be electron charge per unit length. Okay, times the velocity in the x direction as a function of x. Okay, so let me do that. So let's say the velocity of electrons, which you already know from previous discussions, is just equal to minus a mobility times that electric field E sub x. Okay, so down here, to finish this picture here, I'll call this E sub x now. Oops. I want that to be green. And let me also define my x direction. So to do this problem, I'm going to have to define a coordinate system. So I'll come down like this, and this will be my x direction here. And on this, let me define that as 0, and let me say that's L. So the length of this channel is L long, basically in this. Okay? And so that's my x. So when I say Q prime of x, I'm saying whatever the charge is at some location x along that axis. Okay, so I could say Q prime at L, and that would be whatever the charge is at that location. Q prime at 0 is whatever the charge is there. You notice my velocity is also a function of location as well. Okay, so all of these things I'm going to take into account when I get my current here. And so that's what I'll do next time. So just formulating this current equation. Next time I'm going to tell you what Q prime of x is, and I'm going to tell you what the velocity of x is. And Q prime of x is going to be as simple as just what I started out with. It's just going to be this. I've got charge across a capacitor. Okay? But we're out of time, so let's stop here, and then I'll see you on Monday. I guess one thing I should say that I should have said in the beginning, next week I'll be here Monday and Wednesday, but on Friday I'm going to be gone. And on the Monday after that I'll be gone. And that's on your schedule, actually. You can see those by the asterisks there. But I'll be back next Wednesday, and then you got your midterm on that Friday after that. Okay? Anyway, I'll say this again at the beginning of the next lecture. But everyone have a good weekend.